Let us start the today's session with the next clock logic family circuits, that is differential current switch logic. Before entering into that, let us recap what we studied in the previous class. So the previous class we started with the clock logic family. That clock logic family usually be faster than the static logic families. So then the domino here, the clock logic family here, they are having some two different kind of circuits. Either one is the domino logic family, the other one is differential current switch logic, by shortly called as DCSL. Then we studied the domino logic family. In the domino logic family, there's a general circuit. We took an example. So the operation of domino logic will be, the mode of operation will be in two phases. The one is in pre-charge phase, the another one is evaluation phase. During the pre-charge phase, the pre-charge transistor, that is nothing but your PMOS, the pre-charge transistor will be like in the top. So that will be pre-charge your the capacitor. So during that it won't evaluate, means during that time, during the pre-charge time, even if we give the input, the circuit will not behave. It won't produce any output. But during the evaluation phase, what will happen? It will evaluate your inputs, then it will produce the output. So that is why I said here, when the clock is equal to 0, when the clock is equal to 0, it will be in the pre-charge mode. When the clock is equal to 1, then it will be in the evaluation mode. So here, to implement the domino logic here, how many transistors is required here? Totally we need the transistor 4 plus n transistors are required. Already we studied this, right? 4 plus n transistors. Now here what we did in the sense, especially the output here we connected here one inverter, that is a static CMOS inverter we connected. Then there is a one additional weak PMOS we connected. It is like you might have studied earlier CMOS domino logic. This is the extension version of that domino logic. So now in this, the very important thing is what? Only you can able to implement a non-inverter output or non-inverter logic circuit, only you can implement. Next, what is the role of this transistor, the M2? The role of the M2 is, see example, this portion, the Vout bar here, when I'm having the value is equal to, it's completely charged during the evaluation phase. If the transistors, the pull-down network transistors are in series, what will happen? There is a problem of charge sharing. So when the charge sharing is happening, so the output here Vout will get straight to change, because when the Vout is equal to 1, here will be 0. If it starts trying to reducing, start trying to discharging, then this also will get changed. So this should not change actually. So for that purpose here, we are using the we must, what it will do here, this is always will be on. If it is keep on trying to discharge here, what will happen? So this capacitor will be keep on, it will maintain the stable state, it will maintain the, it will be stable, I can say, it will maintain the logic 1, I can say. That is the reason we are using the weak PMOS over there. Then we have seen the examples like, sorry, here not 4 plus 1, sorry, it is a 5 plus n, right? Because the static CMOS inverter has 2 transistors. Right. Next we have seen like one example, like 2 input NAND gate using this logic actually. Then we studied the advantages and disadvantages. Next, as mentioned, let us go for the differential current switch logic. This differential current switch logic is derived from, I can say, it's a class of clocked differential. It's a class of, clocked differential or clocked, I short already, differential cascade voltage switch logic. In this one, see here, differential cascade voltage switch logic, this one. This will charge circuits. So this will be a generic method that will be applied to the clocked DCVS. That a DCVS means what I can say, differential cascade voltage like switch I can say. Okay. So gets to reduce the internal load voltage swings. Now what I will do here, I will say something. This DCBSL, it is derived from this one it's derived from conventional CMOS logic. Conventional CMOS logic, that is normal CMOS logic, like CMOS logic, and ratioed pseudo NMOS logic. Ratio. So now what is the main important thing is listen, it will combines the advantage of both. Advantages. So what are the advantages of and it will provides what and all it will give. Actually it will provides the first one is like when I combine both, it's like a high speed, the circuit will be more speed, then your area will be efficient because you know that ratio to pseudo NMOS will be like a less area, then conventional CMOS will be very faster, then rail to rail. Rail to rail logic. Rail to rail in the sense meaning is VD to VSS. That is the meaning of that. That is the meaning of rail. Power rails telecom to VSS. Logic design. That will be all total. Okay, so now the DC VSL is a ratio logic. It is a ratio logic. As I mentioned already, it is a ratio logic style that completely it will eliminate the static current and it will provide the rail to rail swings. Means it will provide the range of voltage from VDD to VSS. Then it provides a much higher functionality with a great fanning than the conventional logic. More fanning, we can able to use it with the help of this logic circuits. So this high functionality will give you the number of logic levels and the gate output nodes to be minimized. So now next thing is I can say this will exhibits the higher power consumption due to pre-charge differential nature of the output, because the output here will have both outputs it will produce, in the sense non-inverted output and the inverted output. That is why you can call it the differential nature of the output it will produce. Now let us go to the main thing is from that the family one, as I mentioned, is a differential current switch logic, DCSL. That is only you can call this DCSL, differential current switch logic. This differential current switch logic is a clocked DC VSL logic style that will be the capable of implementing the gates with high fanning. High fanning in the sense we can mention the more number of inputs it can be able to drive. Then it will achieve the low power by restricting the internal voltage swings in the NMOS evaluation phase. So let us see the diagram. I will show the diagram. Then so like here, as you know that we are going to work on pre-charge and the evaluation phase, right? The pre-charge will be high, the pre-charge low, and improved pre-charge low topologies are possible. Here total 3 we are going to see. The one is nothing but the pre-charge. When the pre-charge is high, how it will be like when pre-charge is high means what? Clock is equal to 1. Was like the circuit during the pre-charge it will be high, next pre-charged low and improved pre-charge low topologies. So this pre-charged low has a superior performance compared to these two architectures. Totally three different architectures we are going to see, or three different diagrams we are going to see in this. Okay. So now later we will see what is the problem with this structure. Before that, let us go for that. This is the first structure. There's a first differential current switch logic 1. Okay, you can see this differential current switch logic. Now you can see this structure. Watch carefully over there here. What and all is there? Okay. First, you can see in this structure that pre-charge high DCSL. This structure pre-charge high. This is first is pre-charge high structure. Actually, it is pre-charge high. It consists of NMOS evaluation tree. This only. NMOS evaluation tree. This only. This NMOS tree we are having. This is for your evaluation. NMOS evaluation tree. It consists of evaluation tree. Next, it consists of one cross-coupled inverter. So where is a cross-coupled inverter? Just I will show you. You can see this. See this portion, you can see. This will be a cross-coupled inverter. Cross-coupled inverter in the sense like this. The diagram is like this. The inverter, one of the output is driving the another inverter input, and this inverter output is driving this inverter input. This is what here. Okay, that is the one. Next thing is the cross-coupled inverter is okay. So if I want to say the cross-coupled inverter pair, the transistors are, which are the transistors? T2, T3, T6, T7. See, these four transistors are cross-coupled inverters and the pre-charged transistors. Which and all is the pre-charged transistors? So here the pre-charged transistors are T1 and T4. See this. So what I will do, I will take it as this. Okay, this T1 pre-charge P I will make, T4 this also I will make P. That is pre-charge transistor. You can see where it is connecting. It's connecting to the clock. You can see this. It's going, the T1 is connected to clock. The same, the clock you can see here, it's going over there and is connected to T4. So the pre-charge transistors T1 and T4. Now next you can see that T5 and T8. The transistor T5 and T8. What will do? So this T5 and the transistor, the presence of T5 and T8 is what differentiates this gate from other DCBS logic gates, the T5 and T8. You can see this T5, T5 and this T8. You can see the T5 actually where this gate we are getting from this, from the inverter it is driving, correct? No? So you can see this is the inverter output, right? From this only it is driving. Same the way this T8 also is driving from this inverter input. This input we are getting from the output. You can see it is like it is driving from the previous output. Correct? Now same the way even here also it is driving from the Q bar. You can see this T5 from the Q bar is going. So the Q bar, you can see that line actually. The Q bar, it is connected over there. Then same I can say this is the Q bar is connected to over here also. Then you can see that same thing is going, the gate will be T5. So I can say that T5, T8 is nothing but what it differentiate this gate from other DCVS logic gate. Okay, from the other logic gate it will drive. Okay, let us see the operation of this circuit. Okay, how it will operate first. Okay, now the operation of the gauge start with clock is equal to low first. Okay, when this clock is equal to low, when I apply the clock is equal to low, okay, clock is equal to low. When the clock is equal to low, what will happen? The transistor T1 will be on. Okay, it's just wherever it's going, just I will put the transistor. Okay, the transistor T1 is on. Next, the transistor T4 also it will be on. So when the transistor T1 is on and the T4 is on, now again we can see wherever it's going, only those two only, we are not having any more else. So now automatically what will happen? This is VDD, correct? This is a VDD. This is VDD. Now I can see what will happen when clock is low on the node and the Q. We can see this name. The Q here we are having here one CL capacitor. You assume in this way. Okay, you assume in this way. You are having a capacitor. Now what happened? We can see when the clock is equal to 0, the T1 will be on, the VDD will flow over there, then the Q will be charged, correct? No? The Q will be charged and the Q bar also will be charged. So I can say when the clock is equal to 0, the Q and the Q bar is charged high, means it is 1. Correct. So when it is 1, if it is when it is charged high, the gate evaluation begins with the stable inputs. This is pre-charge state. Now you understood the pre-charge in the sense it will pre-charge the transistor. So the Q and the Q bar both the places are charged with the high states. Now what we will do, this clock is equal to 0 means it is in which phase actually? It is in the pre-charge phase, right? It is in the pre-charge. So pre-charging is done. Okay, next what we will do, let us see when the clock is equal to 1. When the clock is equal to 1, so it will be in the evaluation mode. So evaluation mode in the sense of, so here the input should be stable. So inputs are stable in the sense what is the meaning of that? So where the inputs, so this only the NMOS tree is there, no? So here only you are passing the inputs. So even you have to change the inputs here only you have to change and we can perform that. So now gate will evaluate with the stable inputs to the NMOS tree and the clock is going high. Okay. Now the clock goes high. What will happen? The clock goes high. So what I will do, I will take the same figure because this is for clock is equal to 1 because I will show evaluation phase. So you need to know in the previously what happened here, the Q is pre-charged fully, correct? No, so it is pre-charged, it is 1 actually, it was 1. even here also, because during the pre-charge phase, even this also was 1. This will be your VDD. Okay, so now when the clock is equal to 1, so this is what we are going to apply. This is equal to 1. When the clock is equal to 1, now we see, so which are the transistor will be on now. So let us put transistors, which are the transistors will be on now. When the clock is equal to 1 means it will go over there. This is 1, this will be off. Okay, fine. Then you can see this is going for this gate. So the transistor T9 is on, correct no? Then transistor T10 is on, then this transistor also is on, then this gate is going over there. Now we can see when this transistor is on, this is on, next what will happen, this will be a 1, correct? So here the Q is equal to 1, in the sense we can see here this Q is equal to 1 means for this inverter here this is 1. If this is 1, in the sense this is the inverter, so this inverter the output will produce as 0 over there here in this place, correct no? So or I can say like if this is 1, this transistor will be on. If this transistor also 1, then what will happen? You can see the position, this is 0, then this will be 0 in the sense, so this is driving the other inverter, so this is driving that anode, right? That, so this will be your 0, when it is 0 I will get as 1 over there here, when it is 0, so I will get as 1, when it is 0 this P transistor will be on, correct no? This is 0, this P transistor will be on, I'll get as 1 over there. Okay, now we can see in this place what and all has happened now. When the clock is high, then T9, as I mentioned here, you can see this T9, T10 and the T11 is on, as I wrote earlier, right? Next, while the Q and the Q bar being high ensures that Q and the Q bar will be high. Q and the Q bar is high. So this will ensures that T5, T5, T6, where is T5? See here, T5, T6, T7 and T8 is on actually. So T5 will be on because this is 0, not 0, because earlier it was 1, right? When you are during that clock cycle, don't think about this. Earlier it was 1, then this is 1, then that is 1 means, so even this also will be on. Sorry, not this. Okay, this is on. Then T5 is on, T6 is, T5 is because even, yeah, this also on, T6 also on, T7 also on, then even T8 also will be on because this is 1, because the Q will be 1, this portion you can see, this is Q is 1, then here the Q bar is 1, so just that value over it will go, then T8, even this also it is 1, I will get a T5, T6, T7, T8, it is also on. Then what will happen? The Q and the Q bar, if it is on, then the Q will try to discharge. You can see that is the direct path. You can see here. See, there is a direct path from this portion, correct? There is a direct path over there. Then what will happen? Then the Q and the Q bar will be discharged towards ground. Towards the ground through which transistor? Towards the ground through T6, T7 and T10 through T6, T6, T7 and T10. See, this is T6 is on, T7 is on, T10 also is on. Then automatically what will happen? It will discharge through T10 actually, the Q bar. Okay, so it is discharged. Next, the discharge of the Q and the Q bar is not symmetrical. Why? Because the discharge in the Q bar will not be only through this one it will discharge, but you can see the other place, the T9 and T11, it will enter into the evaluation circuit here. You can see it is so it is not symmetric actually. See here you can see T9. So what we can say in the sense, the discharge of you can say the discharge of a Q and a Q bar is not symmetrical. It is not symmetrical because of NMOS tree will assure one of the output here NMOS tree this one, right? One of the output voltage differential in the right direction. So now here we can say once the inverter switches, here we are having two inverter couples are there, right? So once the inverter which it's not symmetrical because output say assures that one output say the Q has a stronger path to ground actually. Because the NMOS tree assures that one of the output say anything Q or Q bar, right? Q has stronger path to ground actually. So this may cause the Q to fall faster than Q bar sometimes. Now the cross-coupled inverter function is a sense amplifier only. Why? Because the sense amplifier will sense exactly the logic of 0 or 1. Why? Because due to the charge sharing problem, you know that wherever the internal capacitance will be there, here we are having the loading capacitance. So what will happen? There will be some issue will happen over there, whether the output has to produce either 0 or 1. So what it will do, with the help of the inverter pair only, it is like kind of a sense amplifier. So your inverter, which one? The inverter pair actually. So I can say the cross-coupled inverter function. The cross-coupled inverter function The cross-polination access, it will act as a sense amplifier. That is the meaning of that amplifier, and it will boost the output voltage difference. And it will boost the output function. Right direction. So now here sometimes what will happen, so one of the inverter switch, which will, the switch threshold will be crossed by the Q and the Q bar swings are high. Now at the time what will happen, the low going transistor, which one, this one, see here sometimes what will happen now, here in this output, here we may have the one capacitor, here we may have the capacitor, see here, there again wherever we are having the internal node, there also there is a capacitor. So what will happen, we try to discharge over there. So that is the reason we are saying here. So in a rising node of Q bar is isolated from the NMOS evolution tree. So this will limit the charge up of internal nodes. Wherever you are having the internal nodes, it will limit the charge in the NMOS tree actually. So it's like in DCVS circuits where NMOS pull down tree is never disconnected from the output actually. So here very important thing is you can say, so NMOS pull down, this is pull down, right? That is only NMOS tree. Pull down tree is never disconnected from the output. The output, because this circuits will charge the internal node. It will charge the internal node up to what actually, the internal node of the NMOS tree up to VDD minus VTH, where we know the VTH is the threshold voltage of NMOS transistor and the VDD is the power supply voltage actually of the NMOS device. So here we can say in contrast to the DCL, differential current switch logic. The DCSL means differential, right? So now I can say DCSL. So the DCSL will charges the internal node to much smaller voltage. Much smaller voltages doesn't simply example if the supply voltage is 5 volt, then the order of 1 volt with the supply of 5 volt, the gate will comes to the rest in a start with Q will be low and the Q bar will be high. Then the transistor T12, here you can see in this diagram, one dotted line will be there, this one, this transistor T12, this one actually, this may record, it may record, okay, so just I will specify here, it may record, when actually it may record to provide charge buildup. So charge buildup on the internal node of the gate. So now on the completion of this evaluation, this is the evaluation stage. It will evaluate, then it will produce the output. On the completion of the evaluation, the fact that the high output in the Q bar, that it's Q bar in the previous state, example, because in the previous state the Q bar will be 1 actually. So that will be disconnected from the NMOS tree, that will assure that the further changes in the input do not propagate to the output. input. So this is like you can say compared to your CMOS logic style. So in the CMOS logic style, what will happen? Where the changes in the input of clocked logic, it will cause the DC current, like or the gate output being destroyed. So like compared to that, here we'll have like we must to adhere strictly to design the constraints of the building of DCVS NMOS tree is no longer required. The gate inputs may cause path to ground in both half of the NMOS tree. However, so we need to assure that the one of the path has a stronger pull down other than the any one of the path will be stronger actually here to allows the DCSL gate to evaluate its input. So on the completion of the evaluation phase, there is no static current path. Completion of evaluation, I can say the completion of. So during one clock cycle, if you take, the evaluation will takes place when clock is equal to 1 actually here. The completion of the evaluation, no static current. There is no static current path from VDD to ground. So this circuit has strongly driven outputs in all the phases of gate operation. So now here we are taking the example of the completion signal may be generated by taking a NAND of two inputs. By taking a NAND of two inputs. Two input NAND gate. Okay, so the previous here we shown no, in the structure. So here just we'll have the modified diagram like see this figure. The figure shows that uh, it's a pre-charge low DCSL actually. So this is second circuit. So here in this you can see the addition of transistor the T5 and the T8 compared to the previous one. You can see here. Here we are having that same diagram. Just you can see the what the difference we are showing here. The additional thing is we are having a pair of inverters here. Actually, we are having the pair is nothing but here inverter pair. Okay, so cross coupled inverter pair. Cross coupled inverter pair. What are the transistors? T2, T3, T6, T7. Next you can see the additionally we are having the one the pre-charge transistors here. Which is the pre-charge transistor here? Pre-charge transistor for T1. That T1 is a pre-charge transistor. Okay, then which is the evaluation transistor? Which is the evaluation transistor now here? It automatically one is the clock will be is equal to 1 when it goes, then T9, correct? T9 actually, T9, the T12 actually it is a hidden we are given, yes, T9, then which is one more, you can see this clock is going trying only this, correct? So same this clock, see the line is going over there, and T10, so I can say the evaluation transistor is T9 and T10 is evaluation transistor. You can remember this circuit how it look like. Normally your this circuit, right? See, we'll have kind of the pair of inverters here is there. Then this one, CMOS domino logic. You might remember. See, we will have like this circuits. So here it will be clock will be there. This is the PMOS. Here is NMOS. See, same. PMOS is there. The NMOS here we are having. The cross coupled inverter we are having. Then here the addition of the transistors like here we used the T5 and T8. Additional transistors. The additional transistor is here the T5 and T8. So this will increase the capacitance of the output load. This T5 and T8, these two will increase the capacitance. Increase the capacitance of the output load. Because you can see here, what is connecting over there, we will have the output capacity here. This and this, we will have the capacitance here also to be there. And even here also we will have the capacitance, internal capacitance. Then the Q, here we will have the capacitance. Here also we will have the capacitance. So like this, it will be there. Here we will have the NMOS tree structure like. Okay. Now what we'll do, we need to decouple the NMOS tree from the gate output. Gate outputs will reduce the effective internal load capacitance seen at the gate output. Here the gate become increasingly better than compared to previous some methods would be there in terms of power consumed and the propagation delay as the NMOS tree higher rises. So compared to the previous under, so this will have in terms of power consumed and in the power propagation delay for NMOS tree. Now what we will do here, like in the previous discussion, what we did in the previously, we took the differential current switch logic with the outputs are pre-charged high. That is what we took in previously. I think you remember right. See here, what you did in the sense, you are pre-charged here with the high. Now you make an assumption here, you are going to pre-charge with the low. Simple, make assumption. That is what here we are going to do here. What we are going to do in the sense here, the previous cases, the outputs are pre-charged as high. Then here what we are going to do, the outputs are pre-charged low. Which outputs? Outputs in the sense the Q and the Q bar. These both we are going to pre-charge as low. That means 0, then this value will be 0. We are going to pre-charge as 0. So in the sense it is I'm not applying initially as clock is 0 or 1. Okay, straight away I'm giving a clock is equal to 1. We are making an assumption as it is pre-charged as Q is equal to 0 and the Q bar is equal to 0. That is the meaning of that. Now here it is like the circuit will be pre-charged state with the Q and the Q will be low value and the clock is high value. That is it. So only we took. Output pre-charge is low means the Q is equal to Q bar is equal to 1 when clock is equal to high. So now when the clock is equal to high, it will be in which mode? When the clock is high, it will be in the evaluation mode. It will be in the evaluation phase or evaluation mode, I can say. So the circuit will evaluate with when the clock is high. So since initially the gate outputs are initially low, the gate outputs are initially low, you have to assume. So next, the NMOS evaluation tree is disconnected from the gate. This one, NMOS tree disconnected, because we are assuming that initially the outputs are this outputs. This output initially it is 0 as initially. Okay, output 0 means initially the gate outputs are 0. Or 0. So then what will happen? The NMOS evaluation tree or N tree, you can say. NMOS evaluation tree is disconnected. It will be disconnected because of 0. It will be disconnected from the gate output by T5 and T8. You can see the T5 and T8. Where is the T5 and T8? This only. This will be disconnected, the gate output, because both are 0. Q also is 0, then Q bar also is 0. So what happened? The gate will be disconnected. So I won't get any value over in this place actually, because this portion, you can see this is 0, right? Then even this also 0 only. So the NMOS is open, both are is open. So then automatically this NMOS tree is disconnected, I can say. Now the circuit is enter into the in the starting. This is in the starting state. If the circuits which enter into evolution mode, when it will enter into the evolution mode, when clock is equal to 0 only. Why? Because it is 0. You can see, because now you assume that initially what I said, we pre-charge with the 0. If I pre-charge with 0, what happened? So your NMOS evaluation phase at the tree circuit, it is not playing a role actually. So now it's entering into evaluation mode with clock goes low. Now if the clock goes low, automatically what will happen? Then that capacitors will be charged, correct? No? Since the evaluation will starts only after the output, when the evaluation will start in the sense the output will cross the VTH. When the evaluation starts, the evaluation starts at when it start, your V out will be, or the V out should be after the output will be cross the VTHN. Then only the gate propagation delay will be degrades. This is about the second circuit. Next, similarly, we are having like there will be some improved pre-charge low actually, because this is we consider as the circuit as pre-charge low circuit actually. Now the improvised version, it's like I'll go for the improvised version. The third is like an improved pre-charged low DCSL circuit. So how this circuit will be there, you can see the compared to that and this, the changes will be you can see this is your improved version. Now you can compare this to the previous one now. What are the changes you can see now? Again, we are having the inverter pair. The inverter pair is this, correct? The cross-coupled inverter pair pairs are T2, T3, T6, T7. Then here we are having Q. The Q will have, here's example, the capacitors, right? The Q bar also will have the capacitors. Then this is the clock we are having. We can see additional transistor. You can say which is the additional transistor here we add. This is the additional one we are having, right? Now the T5 and T8, which is connected to the NMOS 3 circuit, I can say here. Now in this we can say this circuit will have some better speed characteristics. The improvement will be obtained by removing the pull down transistors T9 and T10 where from this previous diagram. Removing this T9 and T10. Which one? This one. See? T9 and this T10, it's removed. This both are removed for next diagram. Okay, I say nothing else. Then additionally we added the one transistor which is removed. Additionally one transistor is added here. You can see this T9 here we added here. So which is removed the pull down transistor T9 from the previously, and we are replacing by the single transistor N. So that T5 so this one will be replaced one. So this is the new one, okay, from the previous one. So we connected with this. Now we can say the gate operation will be starts with again the clock is high. Now gate operation starts with clock is high. Okay. Now the clock is equal to 1. If the clock is equal to 1, what will happen now? We can say this T9 is on. Okay. Next. Then where are we going? So this is only it's on. T9 only it's on actually. T9 node, right? That if it is means then T9 is on, and the node Q and Q bar is equalized. The node, the Q bar are equalized. Because when this is on, what will happen? When this is on, this value we need to know. This value means this only, right? This value, the output of this here. This is the output of this inverter. This is the output of this inverter. You can see here we'll get. Should be equalized means it can be like what is the value here actually? Initially it is like a 0. This is like, because it is an improved version of the previous one. Improved or previous version means the previously we started with the pre-charge with 0. So even this also will be 0. Both are 0, 0 here. You can see this. This improved. Right? So starts with the node Q and Q bar is equalized. So in addition, it will cause us to have the T5, T6, see T5, T6. Okay, sorry, clock is equal to make it as 1 better. Okay, 1. Because initially we said as 0. Okay, later after that what we did, we made when clock is equal to 1, then the Q will and Q bar will be equalized with the 1 actually. When it is 1, then here also will be 1. Then this T5 will be on, correct now? T5 will be on. Then the T5 8 also will be on. Then the T6 also will be on, because see this one. Then T7 also will be on. So T5, T6, T7, T8 is on. So it is equalized. Equalized means I'll say it is 1. Okay. So now we got on the gates drains are connected. Now we can say the Q and Q bar, it has the path to discharge directly. We can see this is means if I'm having this way, it will start to discharge here. You can see that there is a path to discharge. So I can say here the Q and the Q bar, the Q and the Q bar discharge to a voltage at VTN or lower through which transistor actually? Through T6, T7 actually. Okay, it will limit the discharge voltage of threshold voltage for lowers the power dissipation, which is compared to DCL2 previously. Compared to DCSL2, that is the previous one. Compared to that, compared to that, the performance is good. Additional performance wise is marginally compared to the performance improves actually here. Performance will be improved at the same time marginal because of smaller output. The voltage swing will be needed at the output. But in DCL1 and DCL2, the previous two cases actually, the outputs are not always one. In DCSL1 and DCSL2, the outputs are not always one. They are actually always, because of it will be like it will try to discharge. But the evaluation will be starts with the low going clock. On the transistor, the switches T1 will be switch on, and the charges, the output nodes will be high through the T2 and the T3, so which are on because of the existing low voltage pre-charge at the outputs in the previous cases. So now here these are all the some important the observations we made in this the improved pre-charge differential current switch logic.